Hello and welcome to a video about modeling with quadratic functions. So there are lots of different quadratic functions that you can model different situations with. The one I decided to use was the one out of our textbook that talks about the height of an object falling under the force of gravity. So for an object tossed vertically from an initial height of s0 feet, okay, so this is just your initial amount of feet. Don't worry about those little subscripts. With a velocity of v0, again, that's just a value there, feet per second. The object's height at time t in seconds is given by the formula h of t equals negative 16t squared plus v0 t plus s0. Now you might be looking at this equation and thinking, well, there's a lot of variables in here, but that's not really the case. So this v0 and s0 are parameters, and those will be given to you in the problem. So you should be able to just work from there. Okay, an example in action here says a ball is tossed vertically from a deck at an initial height of 15 feet and with an initial velocity of 30 feet per second. Okay, so that means right here, this 15 feet tells us that our S0 is 15, and this 30 feet per second tells us that our V0 is 30. Okay, so let's go ahead and plug that in. So h of t is going to equal negative 16t squared plus 30t plus 15. Okay, so that gives us our equation. So now we want to use a graph to estimate when the ball lands. And then we're going to also talk about how we could find this exactly. Okay, so estimating when the ball lands, let me kind of draw out a rough graph of this. We'll look at Desmos here shortly because mine's not going to be very accurate. So looking at our c value, this constant back here, we know that our y-intercept must be at 15, so it's got to be somewhere up here. Now maybe that's our vertex, but I'm guessing not, right? So that means the ball must be going up and coming back down. But because it's a parabola, it's also going in this direction. But in real world, or in real life, this negative part over here doesn't make any sense. So the ball lands when it hits the ground, right? So when our height is 0. So that means we're going to be looking over here for the positive x-intercept. Okay, let's hop over to Desmos. So I've already got this function entered in, but then I didn't do anything else because this can sometimes be the most frustrating part of working with these problems. I don't see anything on the graph. I mean, yeah, I can answer this particular question, but this doesn't even look like a parabola, right? It looks like a line and a line. So a couple things you can do here is you can try to, zoom out and stuff. Okay, that's not so bad. Or you can even go over here into the little wrench thingy here, and then you can actually change the values of your x's and your y's, right? So like right now my x's look kind of goofy because they're really big. So I want to change that and change that to a 5. So now it looks maybe a little bit more parabola-like, okay? All right, but remember what question we were answering. I sometimes get distracted. We were looking for the positive x-intercept. So yes, there's a negative one back here, but we can't go back in time. So I'm looking for this point right here, and Desmos is so nice because it then pops a value for us. So 2.285. Maybe the decimals go on a little bit longer. Who knows? Like sometimes Desmos doesn't always give us everything. So let's see if I can remember that value and go back into here. So we can say, see my blue pen, after 2.285 seconds. Okay. How would we find this value exactly? Well, I said that's when the height is 0, right? So we'd have 0 equals negative 16t squared plus 30t plus 15. And if you watch the properties of quadratic functions video, we know then that we'd want to use the quadratic formula. Okay, I'm not going to do that here because, you've already seen that once. You don't have to have me show you it again. But I just definitely want to make sure we talked about that here too. Okay, beautiful. 2 questions. We know these questions go on for a while, so let's see what else we got. I went ahead and brought down my equation that we had up here. I went ahead and typed that out just so I didn't have to try to remember it. Then we want to determine when the ball reaches its highest point. Okay, so because this a value is negative, my parabola opens down, as we've already seen. So then we know it's going to reach its highest point at its at the vertex. See, I keep forgetting to grab my blue pen. What's happening at the vertex? Okay, this doesn't say exactly or approximating, but since we did it on the graph last time, let's do this one using algebra. So that means my t is going to be, ooh, does anybody remember that vertex formula to figure out my input value? I hope so. So it's negative b over 2a. So in this case, this would be my a, this would be my b, so this would be negative 30 divided by 2 times negative 16. Okay, so that gives me 30 divided by 32, and then if you wanted to simplify that, you could. I mean, we could say this would be 15/16 of a second. And that's exactly what the question wanted, because it wanted a when answer. Now, if it asked me how high it was, then I'd have to do some more, right? I'd have to take this 15/16 and plug it back into our function, but it didn't ask me that, so don't have to worry about that one. Fabulous. All right, the last question here we've got is compute the average rate of change of h on the interval from 1 to 1.5. Hopefully you've been practicing your average rate of change equation, because we're going to need that here. So remember that our average rate of change on this particular interval would look like h of 1.5 minus h of 1, all divided by 1.5 minus 1. Okay, so dealing with decimals can sometimes be a little bit messier. So I'm going to pop over to Desmos again. Go back here. I've defined my function to be h of something, you'll notice. So that means then I can type in h parentheses of, oopsie, I don't need that one here, 1.5. And then Desmos will give me a value, okay? While I'm here, I'm also going to type in h of 1. H of 1. And then Desmos will give me a value there too. Now, if you really want to be fancy, you can type in the whole h of 1.5 minus h of 1, all divided by 1.5 over 1. But I'm not going to do that. So 24 and 29. All right, go back to my screen here. So we said this is 24 minus 29, all divided by, that is 0.5. So this would be 5 divided by, oops, negative 5, right? 24 is smaller than 29. I'm going to change this over to a fraction of a half. So that means this is going to be negative 5 times 2 over 1. So we get a value of negative 10. Does a negative make sense here? Well, I don't know. If we think about the graph, oops, let me pop back over here to Desmos. So we said our vertex was where? Was here. So 0.9. So yeah, it does make sense because 1 is going to be, I don't know, somewhere in here maybe. And then 1.5 is going to be maybe somewhere, not quite over there, maybe in here-ish. So yeah, a negative value certainly does make sense because as we talked about before, negative average rate of change means that your function is decreasing. And that totally makes sense here. Okay, so there's our average rate of change. Include units on our answer. Oops, I didn't do that yet. Okay, so our units of our numerator, h's units are feet. So this is, oops, I got to change my color again. Feet per, because remember average rate of change is always something per something. My denominator's units, those are my time, so that's in seconds. Okay, so write one sentence to interpret its meaning. Oh yes, interpreting. We're going to be doing that a lot. So we already said because this was a negative, that means it's decreasing. Okay, so we can say on the interval from 1 second to 1.5 seconds, the ball, I had to remember what we were throwing here. Let's see, the ball is decreasing at So because I said the word decreasing, I don't also want to say negative here, right? Because the decreasing part is telling us that it's negative. So we're decreasing at 10 feet per second. All right. Hopefully this helps with these problems. They can sometimes look monstrous because they go on for a while, but really all you're doing is just picking up information that we've already talked about. You just have to put it into a context of the particular problem. Excellent. Thank you for watching.